Okay. So, hello everyone. Thank you for joining the HPSC webinar for 3rd of March 2025. We are happy to welcome E. Zhu and a little bit about him. So, E has recently obtained his PhD from National Institute of Scientific Research in Montreal, Canada, INRS, and he has started the position as an applied scientist at Reality Defender, which seems to be doing quite a lot of work, cutting edge work on deepfake detection in audio and other modalities. His research focus on representation learning and application for human-centric signals, such as speech and physiological signals. So it's very interesting to see his webinar today. And the topic of the webinar is generalized audio deepfake detection via style linguistics alignment pre-training. And the webinar duration would be 40 minutes. After that, you are free to ask questions. Please, I request you to mute your microphone till the E's talk is finished. And I welcome. It's a great honor to welcome E today. So I let the floor to E. Please go ahead.
All right. Hi, guys. Thank you for the introduction, Brish. So, so I'm E, and I'm right now an applied scientist at Reality Defender. And today I'm going to give a talk about one of our recent models, which we focus on making the audio deepfake detection models generalizable across different attacks. And we do this by style linguistic alignment pre-training. So if you have any questions during the talk, feel free to drop your questions in the chat. I'll try my best to answer them at the end of the presentation. All right, so what we're going to cover today, I'll firstly give a very brief introduction on the background of this work. So, for example, what are the state-of-the-art models and why exactly do we want to do this new type of pre-training? I will then dive into some details about the system, model architectures, training strategies, and so on. And then I will provide some details about like basically different experiments that we did, which includes the results that we have in the NeurIPS 2024 paper and our submission of this model to the ESV Spoof 5 challenge, and some of the takeaways that we see like basically when we deploy this model in the real world scenarios. All right, so first of all, about this deepfake detection problem. The problem is quite simple. So let's say we have a speech signal coming in. It can be, let's say, a recorded voice. It can be an incoming call from some customers, etc. And the goal here is to tell basically if this speech is synthesized or manipulated by a generative model, or is it from a real human being? And now, like looking at this problem, it's very much similar to, I would say, all sorts of classification tasks. But for deepfake detection, there are mainly two challenges that people are tackling with. So the first of all is how do we make the system to be more generalizable across different attacks? So here by attacks, I'm referring to, let's say, either new or unseen generative methods. And another challenge that we see oftentimes in real world scenarios is the interpretability. So we can have, let's say, 10 different models that give you very good performance, but in the end,
Wait.
I'm sorry, I heard someone saying something, or?
I request everybody to please mute yourself during the conversation, during the webinar. I think you can go ahead.
Okay, no worries.
Sorry.
Yeah, but just in case if you guys have any questions, drop in the chat. I'll try to answer at the end. So the other challenge is about interpretability. So basically, when let's say we have different decisions returned by different models, we're trying to compare them and to see which one gives the correct decision. We will need to understand at least what information the model relies on to make certain decisions. But what we have found is that this is kind of quite hard for a lot of these models. So for this work, we are trying to tackle these two challenges at the same time. Okay, so to probe a bit more into a typical pipeline for deepfake detection methods. So usually, let's say you have this waveform coming in. It could be just a raw waveform. It could be some other representations of speech, spectrogram, male spectrogram, etc. We usually feed them into what we call an upstream encoder. So this upstream encoder is usually pre-trained in a self-supervised manner. So let's say you have the choices of, let's say, wave2vec or wave-LM or Hubert. So these encoders would basically output what is usually called a universal representation that captures basically different aspects of speech, say speaker attributes, speech content, emotion, and so on. And once you obtain this representation, you can feed it into a downstream classifier to make a final classification to see if this voice is generated by AI or if it is from an actual human being. Now, if we look at basically innovations around this pipeline, we see a lot of success from works that have been focusing on, for example, data augmentations, right? So we have the raw boost that's commonly used for deepfake detection models introduced in 2021. We have other works that have shown success obtained by using vocoder augmentations. And there's another line of works that basically focus on, hey, can we have stronger and more discriminative classifiers, right? So more powerful downstream classifiers that can give us basically better classification performance. And more recently, we have some other works that focus on, for example, you already have a powerful model. Can we make this model smaller? So that's model distillation. Now, for the upstream encoders, you can have different choices. So if there's a way that we can ensemble them to get a better classification performance. And of course, there are also many other tricks that are centered around basically full fine-tuning, right? So apart from that, one question that kind of still exists with this kind of pipeline is that because people are working with universal representations and these large speech backbones, when models are making decisions, we're not exactly sure like what decisions or what information the model is relying on. So there is a group of works that are focusing more on the interpretability side. So you see people now propose these different knowledge-based features, right? So there's some study that focus on capturing attributes about vocal tract, capturing breathing patterns, capturing emotions of the speech so that we can know, we can basically latch onto these knowledge-based features to see if a sample is generated or not. But then usually what we see is that there's oftentimes a trade-off between performance and interpretability. So let's say you can have an interpretable system, you know exactly what the model is relying on, but at the end, the performance is still not as good as what can be obtained from a black box model. And of course, you would say that, hey, even if with these black box models, with these universal representations, we can still use post hoc XI methods. We can obtain saliency map. We can check, for example, which segments from the waveform the model is looking at. We can check which frequency in the spectrogram the model is looking at. But the issue is a lot of these XI methods are sensitive to hyperparameter setup. So each time you use a different combination of hyperparameters, they give you different results. And at the same time, if you compare these different XI methods, you would see sometimes very different results. So it becomes quite hard to know which one gives you the right basically interpretation of the decision, right? Yeah. So what we are proposing here is that we're basically looking at this overall pipeline, and we were asking if there's a way that we can basically learn a better representation in the first place, so that we don't need to spend too much time on data augmentation. We don't need to make very complicated downstream classifiers. As long as this representation that we obtained from this upstream encoder is powerful enough, it should already include a pattern that can tell the generated speech apart from the real speech, right? So, and following up on that thought, we wanted to design basically a new type of pre-training strategy that can help us learn a new upstream representation that can already generalize this better across different attacks, which means that even in the future, let's say there's a new generative model coming out, the representation should be still like discriminative enough to capture those artifacts. And at the same time, we want the representation to be interpreted. So at least we need to know what kind of information is entailed in this representation so that we can understand when the model will make some misclassifications and why this model specifically performs better than the other models, right? So in order to kind of learn this upstream representation, one thought that we have is that if we can find a pattern that is basically unique to real human being speech, then whatever speech that does not have that pattern can be labeled as generated speech, right? So that is like the original thought that we had in the first place. And that led to basically this model, where we basically use the style-linguistic alignment pre-training. So speech is kind of a complex signal that entails different aspects of information. You have, for example, speaker attributes, you have speech content, you have emotions and everything. And one way to decompose speech is to have what we call a style-linguistic decomposition. So the style part, we refer to things like prosody, accent, ethnicity, gender, age, emotion, and other more coerced or utterance level attributes. And we also have another aspect, which we call linguistic, that corresponds to basically what we say, right? So syllables, words, sentences, etc. Now for speech, usually, well, theoretically, we can consider these two aspects to be independent of each other. So who this person is usually independent of what the person speaks. And this is actually a quite widely adopted assumption for a lot of text-to-speech or voice conversion models. So let's say for a voice conversion, what usually happens is that in the first place, you need to somewhat decompose your speech into, let's say, speaker and speech content. And then you can swap your speaker identity with another person's speaker identity and resynthesize your speech. So in the end, you have a new speech that has the exact same speech content as the original speech, but then you have a different speaker identity. And this is for TTS, you have like similar idea there, but all of them have this kind of assumption in the first place where they consider that the style linguistic to be kind of independent of each other. So we looked into the literature, and what we have actually found is that although theoretically they can be considered as independent, it's not actually the case in real world scenarios. So some examples that I give here. For example, we see that people with different genders would use different languages, have different word choices. And for non-native speakers, for example, I'm from China, so usually I would use different word choices. I would pronounce words differently. I would pronounce syllables differently. The sentence organization is different from that of a native speaker, right? And we see all of these differences. For all of these different style attributes, we have the relations between prosody and language understanding. We see that people from different ages would use different word choices and organize the sentences differently. We see this impact of emotional states on word choices and everything. So all of these examples and evidence motivate us to basically think about if we can design a strategy that actually learns what this dependency is between style linguistic for real world speech, we can maybe use that learned representation for deepfake detection. All right, so the model that we proposed, called SLIM, which is an abbreviation of style-linguistic mismatch model, is based on the hypothesis that we assume that the underlying style-linguistic dependency of real speech is hard to model perfectly by existing TDS and VC models. So based on this hypothesis, what we propose here is that we want to use only real speech to learn such dependency between style-linguistic via self-supervised learning. So we don't actually need any labels. We don't need to know, what this person is saying. We don't need to know, the speaker identity. We don't need to know the speech content. As long as we have some real speech samples that are diverse enough, we can learn such dependency pattern. And the way that we want to quantify this dependency is by measuring the distance between your style and linguistic embeddings. And yep, I will get into a bit more details about this overall framework. So for SLIM, we have two stages of training, as you can see here on the left part and the right part. So for the left part is stage one, where we first of all, we aggregate these bona fide samples, so real human being speech from different data sets. And the reason we want to do this is because we want a diversity of speaker identities, of emotions, of different durations of speech, different recording conditions, and so on, so that it's diverse enough to capture the real world scenario. And once we have this multi-source bona fide sample data set, we then feed samples through two branches. So one branch gives you the style information, the other branch gives you the linguistic information. And here, the style and linguistic encoders are both off-the-shelf pre-trained models. I will get into a bit detail later about like which model choice we adopted. But here, let's just assume that these are off-the-shelf pre-trained models, and we keep them frozen during both stages. So we don't change the output representation at all. So once we obtain these style linguistic embeddings, we then feed them into two projectors. So these projectors are very lightweight networks that basically project the high-dimensional style and linguistic embeddings into a lower dimension. And the idea here is that we want to minimize now the distance between these two projected embeddings as to minimize the distance as to make it as small as possible, right? So the reason we want to do that is because we want to align these two subspaces, right? We want them to be cross-correlated as much as possible. So once stage one training is finished, our expectation is that we would be able to obtain a pair of style and linguistic embeddings that are maximally correlated for real speech, but then the distance should be larger for fake speech. So that's like our expectation here in the first place. So once we finish stage one, we enter stage two, which is a very standard, I would say, supervised training framework. We have labeled deepfake or quantify samples. So each speech sample has the label of either fake or real. And then we pass the samples into, again, the same style and linguistic encoder, which we keep frozen. And then the output then pass through these projector networks that we trained during stage one, and we keep frozen at stage two. The idea that the reason that we want to keep all of these encoders and projectors frozen is because we want the output embeddings, the embeddings learned at stage one to be intact, right? We don't want to touch any of those information. And then one modification that we like, one thing to note here is that we don't just use these style linguistic dependency embeddings. We also fuse them with the output from the original style and linguistic encoders. And the reason to do that is because we found that the style and linguistic dependency embeddings are, well, they're learned on a global level, right? So they often capture, for example, for an incoming utterance, if the style and linguistic are aligning with each other or not. So oftentimes, if let's say you have an artifact somewhere in, let's say, a 15 millisecond segment, that kind of details is neglected in the SLIM embeddings. So this is the reason we fuse these dependency embeddings again with the output from style linguistic encoders, because those output are on the frame level, which has all of the temporal details. So by these kind of fusion, we can basically well, obtain the original advantages of these style and linguistic encoders, but at the same time, give complementary information from the dependency embeddings. So for stage two, again, all we train is these attentive statistic pooling layers and the downstream classifier. Now, a bit more details about the model choices. So originally, like in the early work of the study, we also in the nearest paper, we were using wave-to-vec XLS are fine-tuned for speech emotion recognition to represent style information. And we use the same XLSR model, but fine-tuned for automatic speech recognition to represent the linguistic aspect. And apart from that, we also use different layer choices. For the style, we're using the first 11 layers from the SER version of the model. And for the linguistic aspect, we're using the last 8 layers from the ASR version of this model. And the reason we did that is because we have a group of existing studies that have shown that early layers from these universal representations capture more speaker level attributes, whereas the later layers capture more phonetic level information. And that's why we select, these different layers. And an interesting thing kind of to mention here is that for our later submission of this model to the SV 5 challenge, we because there were some restrictions on what kind of models we can use, we need to change the backbone to waveLM base, which is a much smaller model. And in the end, we simplified it to a setting where we only extract the first 7 layers from waveLM base to represent style and the last 3 layers from the same model to represent linguistics. And that also works well. So yeah, I know that this we'll have some discussion about this, but let's just put it this way for now. The idea here is that no matter what kind of backbones we're using, we want to have to have 2 different encoders that captures different aspects of information, right? So in this case, it would be one encoder for style and the other for linguistics. For the stage 1 self-supervised training, this is the objective that we followed. You can see that there are 2 subterms. There is this LD, which is I would say the discriminative loss, where we are comparing basically the SF here, which is the style representation, with the LFT here, which is the linguistic representation. And you can see that we are measuring the distance between them. We're then calculating the Frobenius norm here, and then we're averaging across all the frames. So in the end, what this LD is doing here is that we want to measure basically the average distance between style and linguistic embeddings on a global level, right? So the larger that distance is, it means that these 2 aspects are more further apart from each other. And the smaller this value is, it means that they're better aligned with each other. Now, if we only use this LD term, what would happen is that the model would collapse to a trivial solution. So in the end, every feature in your feature matrix would be basically capturing the same information. So to prevent that from happening, we also have this LR, which is trying to minimize the redundancy of your feature space. So you can see that here we are multiplying the SF with the transpose SF, which is basically give you the covariance matrix of your style and linguistic feature space, right? So the SF here has a shape of batch by feature. So by transpose and by the multiplication, in the end, you will have basically a covariance matrix that measures the correlation between the features. And then we are calculating the distance between that, the covariance matrix, and an identity matrix. And to minimize the distance, what happens here is that we are pushing all the off-diagonal elements in your feature matrix to be 0, which means that in the end, your features are going to be less correlated with each other. So you will have less redundancy in your feature space. So by combining these 2 terms, basically, we have the overall objective for the stage 1 training. For stage 2, I would skip the details because it's pretty standard supervised training with binary labels. So we were using BCE loss, binary cross entropy, nothing fancy there. In terms of model architectures, right? The trainable components for the encoders, as I mentioned, they remain frozen for both stages. The only thing that needs to be trained is, first of all, the projectors at stage 1. So these 2 lightweight networks that are marked with this fire symbol in stage 1, which has in total 2 million parameters. And they are frozen at stage 2. And in stage 2, we only have 5 million trainable parameters, basically coming from the classification heads. So now I would like to dive into a bit more details about our performance. So here is a plot about the equal error rate we obtained on single text. So the idea about equal error rate is that the lower the better, right? The lower it is, the better the model performs. We train all of the models on a pretty standard scheme where we train everything on the SV-Spoof 2019, where we have data labeled either as fake or real, and then we test everything on out-of-domain data, basically SV-Spoof 2021. The in the wild data set basically comprises voices from celebrities in a more noisy conditions, I would say. This AMLAD English version 3 is a newer data set that was released in 2024, which comprises more state-of-the-art generative models, and we were using the English subset from it. So the way we calculate these ERs is that we basically obtain ER per data set and then do the average. So this is why you see these different bars here. For a lot of these models, LCN, RONAT, and this, the Hubert or Wiv2Vec, WiveLM appended with the same downstream classifier, you see them struggling on the out-of-domain data set, right? So ER is around 20, 30%, which is quite high. And if you look at SLIM, when we have the encoders frozen with only in total like less than 10 million trainable parameters, we can already like have the equal error rate, which is already like a very decent improvement. And now we also compare to the method that use full fine tuning. So basically these two orange bars are what would happen if you have like similar backbones, large speech models, and you full fine tune the whole thing, right? You fine tune everything, encoders plus downstream classification layers. And this is what they obtain, which is still higher than what is obtained by our frozen version. And we further show that, hey, we can also do this full fine tuning thing, right? So for stage 2, we can also full fine tune our projectors. We can also full fine tune our style linguistic encoders. And we show that we can further obtain a minor improvement here. And of course, I know that a lot of you guys have experience with these data sets and with a lot of these models. So here I have a more detailed results. I would skip many of these numbers here, but this is the table we have in the NeurIPS paper, which I'm gonna provide the link at the end of this presentation, where you can check the detailed number of these ERs. Now, I also want to spend some time talking about our submission to SV-Spoof 5. So this challenge was organized somewhere in 2024, I believe. So after we finished this model, we finished the manuscript, submitted to NeurIPS, and this happens, and then we get a comment from reviewers saying, hey, can you evaluate on this data set on this new challenge and see what happens? So we did it. The only modification we did is that we changed the backbone from Wiv2Vec XLSR to WiveLM base, simply because there's some restrictions on what model can be used from the challenge. We cannot use the XLSR version. So we did first of all, some cross-model comparison to see which backbone gives you better performance. And the best we have is that basically 13.4 ER obtained by WiveLM base. So this is what is obtained by what they call their progress sets, which is like a subset of their evaluation data. Now we change the backbone to SLIM, and we already see like a marked improvement from 13.4 all the way down to 7.1, right? And we did some ablations on SLIM where we change WiveLM to Wiv2Vec base and see what happens. We also tried different data augmentations, right? Like raw boost, or like raw boost plus some noise, plus some room impulse response and see what happens. Some ablations there. Try different losses. What would happen if we use focal loss rather than BCE, and obtain these different numbers on the progress set. And in the end, we chose one version, which is our SLIM based on the WiveLM backbone using raw boost with BCE loss, and submitted to their evaluation set and obtained a 5.5 basically ER score in the end. I believe this is one of the top ranking models. And one thing to notice that here, we didn't do any full fine tuning. We didn't fine tune the encoders at all. So it's very easy to train. And we didn't use any vocoder augmentation. I want to mention this because if we add vocoder augmentations, let's say you use hi-fi again to augment your training data, and use many other vocoders, you will get another improvement. But here we just want to evaluate how much improvement we can gain solely from this training, this new pre-training framework, right? So this is the number that we have in the end. All right, so those are about the performance. And I do want to spend some time talking about the interpretability part, because at the very beginning, I mentioned that there are two goals of this study. So first of all, we want to achieve better generalizability across different attacks. But at the same time, we want some interpretability, right? We want to understand what information the model is relying on. And one way to do this is that since we have this paired of style linguistic embeddings, and they're trained in a way that we want to minimize the distance between them, right? So our expectation there is that the distance should be higher for deepfake speech and smaller for real speech. And this is actually what we observed on these different data sets. So here I'm showing you this cosine distance on the log scale. This is why the numbers are not are below 0. On a log scale calculated between the style linguistic embeddings and for these 3 different data sets. So the blue ones correspond to the bona fide speech, so the real human being speech, and the orange ones correspond to the generated speech. And the idea is that the higher that distance value is, it means that the further apart these 2 aspects are, right? So this is showing that for real speech, the distance is smaller, and for fake speech, the distance is larger, which means that there's more mismatch there. Now, we're approaching approaching the end of the presentation, but I do want to talk about the misclassification we see from SV5. So we do see that, for example, for the very low intelligible samples, so the ones that was like a MOS score that's estimated at around 1, as is shown here in the plot, the model usually give a misclassification. So it's the robustness to noise still needs to be improved. That's the first part. And at the same time, we did some analysis on a subset of the SV spoof evaluation set, and we noticed that around 10% of the evaluation data, we have an estimation of more than 1 speaker. Of course, there's some false positive cases for sure, but I just want to highlight that for these samples where we labeled multi-speaker, our model oftentimes give a wrong classification, which is kind of expected, right? Because in the pre-training stage, we don't have these multi-speaker scenarios. The model is learned to capture the alignment between style linguistic only for that single speaker, right? So for the multi-speaker scenario, what should ideally happen is that the model should have like a speaker isolation or separation in the first place, and then we do this classification. But yeah, here the general idea is that I just want to highlight the weakness of this model. And just to summarize the takeaways here, some pros and cons when we deploy this model in real world scenarios. So this is evaluated. These are takeaways that we had from basically when we evaluating on our internal benchmarks data sets. We do see that there's better generalizability to unseen attacks. So even if the model is not trained on some attacks, it can still generalize well. We get very good true positive rate, right? So if you want the model to be aggressive, you want it to detect all of the generated samples, it's a very good candidate. And to improve the performance, we don't need to train on generated speech data. So you don't need to craft all the deepfake samples. As long as you have a diverse pre-training data set that covers basically different speaker attributes, recording conditions, and so on, you can keep improving your performance by increasing your pre-training data. And also, if you compare the score generated by Slim to the other models, oftentimes we see a smoother output score distribution. So usually what happens is that for these binary classification models, you have very bipolar decisions. So the model either give you scores that's very close to 1 or very close to 0. For Slim, we see that this distribution is oftentimes more smoother. Well, some disadvantages. Of course, this involves another round of pre-training. So there's a need for guarantee the diversity of pre-training data, right? So you need to have different emotions, different languages, different durations of our speech, different recording conditions, so that it has some robustness to different noises and so on. And also, if I mentioned that this model SLIM is aggressive on true positive rate, at the same time, it is aggressive on scripted speech because it is pre-trained on natural speech. So people are not reading off, speech. So in the end, the model becomes quite aggressive on scripted speech. So let's say if you have a person reading something off, and you feed it into this model, sometimes, I'm not saying all the time, sometimes it can be labeled as deepfake. So that is something that we still need to improve. And there's this also this weakness about multi-speaker data. I don't think there is a very decent way to address this multi-speaker scenario in the pre-training. But I think this can be tackled well simply by having a speaker isolation module in the downstream classification model. All right, so that's the end of this presentation. Thank you all for your attention. If you are interested in some details, feel free to check our newspaper, our submission of this model to SV Spool 5. And if you also work in cybersecurity domain, we have some open positions right now. You can check out the positions using this QR link here. And yeah, feel free to reach out to me. You have my email, my LinkedIn account here. So yeah, so I believe we have reached the end of this presentation. Thank you all for your attention.
Thank you, E. That was very impressive work and very thought-provoking also. So I think we have a lot of questions
Okay.
in the chat box. So maybe we can go through it one by one and
For sure,
try
for
to
sure,
answer them.
for sure.
So Souvik is asking, what is saliency map? It is already answered. How do you determine the objective functions?
Okay. So let me first reverse back to that objective functional page.
Yes, I think the people participants can unmute and ask questions.
Yeah, for
So
sure, for
maybe
sure.
Souvik, you have many questions. You can unmute yourself, and
Um,
maybe if you have complementary questions, you can ask them. Please go ahead.
yes, so Vik here. Can I ask?
Yeah, sure. Go ahead.
Okay, sir, firstly, thank you for this wonderful talk. It cleared a lot of concepts for me. So my main question was about the objective function that you were showing for phase one, stage one. So
Yes.
how did you actually come to that this objective function will work properly? Because for stage two, it is very standard using VC loss and
Yes.
everything. But for stage one, how did you come to it? And also, how did you match the dimensions?
Yeah. So yeah, great questions. So we came from the motivation that we want to measure basically the dependency between style linguistics. So that naturally goes to measure the distance between them, right? Because the smaller the distance is, the more correlated these two subspaces are, right? So that gives us led us basically to this distance measure between these two subspaces. And then in terms of the matching the dimensionality, so the style embedding is a globally averaged embedding, which means that it's a batch by feature, right? Has a dimensionality of batch by feature. And then for the linguistic, it's more fine-grained, so it's batch by feature by time frame. So it's a three-dimensional. So that we need to measure the distance on a frame level, right? So here you see that I'm measuring, basically calculating the distance between the globally averaged speaker embeddings and the frame level linguistic embeddings. And I do this for each frame. You do the Frobenius norm. You then have a distance value per frame, right? And then you do the average. And that in the end gives you this LD term. Does that answer your question?
Yeah, thank you, sir. That was very insightful. Also, one more question I have is that why did you freeze the trainable parameters?
Uh, Let me reverse it back to this slide. Which stage are you talking about? Are you referring to the stage one or stage two?
Stage one, stage one.
Oh yeah, so the original idea was that we want to make sure the style encoder gives you style information, and linguistic encoder give you linguistic information, right? So if we, have them trainable, then there's no guarantee, right? There's no guarantee that there's still disentangled. There's no guarantee that the style still gives you style. Because it's fine tuning on whatever data you feed into it, right? So we do want to guarantee that the output representation
Yes,
from the
sir, I
style
got the
encoder.
point. Thank you, sir.
Yes. Yeah. All right.
Okay.
That's all from my side.
All right. Thank you so much. Okay.
I think Neil has a question. Yeah, E, you.
Okay. Yes, Neil. Are linguistic features temporally dependent in the regularization loss term? They were average put in the discriminative loss. Yes. So good catch. For the LD term, we average the style embeddings and keep the linguistic embeddings as it is. So it do have that temporal dimension. For the regularization term, we average both. So both are averaged on a global level.
Oh, I see. Okay. And why is that? Why do you average the linguistic embedding in this regularization term?
Well, I think my original thought was just to reduce the computational cost. And in the end, I found that this regularization, like we don't actually need to calculate the basically the covariance matrix on the frame level. As long as we have some regularization on a global level, it already prevents the model from collapse. So
I see.
the answer is that works.
Thank you so much. Thank you.
Yeah,
maybe we can go to E. Yeah.
Yeah. Should I see some people raising their hands? Should I be?
Yeah. Maybe we can go in the order in which they have asked the question. So maybe Arth Shah, you can
Yes, yes, sir.
unmute yourself, please. Yeah.
Sir, so my basically question is that you use different types of data set. Once I read MLAAD data set, also ASV spoof different versions of data set. Then the variation in accuracy, maybe is it likely due to the different kind of generation? Like I am confused that in the wild has been generated on GAN-based deepfake. ASV spoof has some MLAAD has some TTS generated deepfake. So, like, what is the reason that what deepfake captures in TTS and in GAN, in voice coder, in voice cloning? What does it capture basically?
Yeah, I just want to repeat the question just to make sure that I understand it correctly. So you're asking that so there's some difference between these data sets, and then the question was what the model is capturing for TTS versus for voice conversion. Was that the question, or was it something else?
Yes, so basically TTS based deepfake there have been generated. Also GAN based deepfake, voice cloning. They change the target speaker. Then what are the properties of that particular machines and which human don't have, or what are the properties that human have and that machine don't have, which your model is able to capture?
Yeah. I think that goes back to the original motivation of this model. We designed it in a way that we want to capture how your one example is how, for example, how your talking habits align with your speech speech content, right? So basically, for each person, they have their speaker attributes, and there is certain alignment between their speaker attributes with what they say, and we want to learn that pattern. So it doesn't really matter if it is a TTS model, if it is a VC model, because in the end, they're definitely changing one aspect of speech. It's either changing the style or changing the linguistics. And there's no guarantee that after this modification, no matter what model you're using, no matter it is a VITS, no matter it is a GAN, as long as you're modifying one aspect of a speech, you break that alignment between style and linguistics. And our model latches on to that kind of dependency between these two aspects to make the classification.
Okay.
Does
Thank
that
you,
answer your
sir.
question?
That answers my question.
Okay, thanks, E. Maybe we can go in this order. So TSTA first, and then Prachi Singh, Carolina, and then Shao. So
Okay.
maybe Style-LInguistics. Can you please unmute
Yeah,
yourself?
it's me. Thank you. Thank you. Hi, everyone. Thanks a lot for this wonderful talk. First of all, is your loss inspired by Barlow twins, a paper by Jan LeCun?
Yes, I'm aware of the Barlow twins model, but not really.
Okay.
Yeah, I don't think I really, try to replicate the losses. I don't actually remember what the loss terms was there. But yeah, here I believe, yeah, I think the thought was kind of simple. It's just I want to measure the correlation between two aspects, and distance seems to be a proper measure. And then I see the problem of model collapse, so I need to design another term to prevent the model collapse, right?
My main question is this. I mean, there are now state-of-the-art text-to-speech systems like 11 Labs or Valley or Play HD that do not seem, at least to me, when I listen to them, to have discrepancy or much discrepancy between style and linguistics. So I was wondering if you've tried your model on such
Yes,
recording.
yes. We did have a lot of these samples in our internal benchmarks. And simple answer is this model works very well. And the second answer is I do agree that because I've been thinking about this question because I've been at least advertising this as hey, we need to align style linguistics. But basically what happens is that I tried different model choices and different layers, and all of those choices seem to work well, which means that maybe we don't really need to specify if it is style linguistic. We need two different aspects of speech that is somewhat disentangled, and we want to measure how they're aligning with each other. So maybe they don't need to be necessarily style linguistics. And this probably also explains why we as humans don't really capture that. Yeah, I hope that answers your question, but I think this question leads to basically how do we open the black box of this model? And yeah, so my takeaway right now is that I do agree that the decision is not 100% aligning with human perception. That's first point. The other thing is that I don't think it's necessary to specify to constrain ourselves within style linguistics. It can be some other aspects as well.
I see. Thanks a lot.
Maybe we can go next to Prachi. I don't think maybe we can cover all the questions, but let's try
Okay.
as many as possible.
All right.
And feel free to please also send an email to E if
Yes.
yeah,
Yes. I have my email at the bottom, excuse me, at each slide. So if
okay.
yeah, all right.
Prachi Singh, maybe you can please unmute yourself. Yeah, go
Hi.
ahead.
Hi, Yi. Thanks for the interesting talk. My question is like you raised concerns about issue with the multi-speaker data. Can you specify, elaborate a bit more?
Yeah, so basically, let's say we your incoming speech has, let's say, two speakers. So let's say it's a conversational speech, right? So it's us talking. And then you feed the whole recording to the model, and you want it to give you a result. It might have some overlap between two different speakers. So in the end, in these cases, Slim would sometimes give you a misclassification. And I think this is somewhat expected in the first place because during pre-training, I don't have any multi-speaker data. And I do believe that the style linguistic dependency should be considered per speaker. So if you have, let's say, two speaker voice overlapped with each other, it's kind of hard. And you extract the speaker embeddings, it would be basically a mixture of two speakers, right? And then it's hard to kind of check the alignment between that mixture of speaker embeddings with your speech content. It becomes quite messy because you have two speakers overlap with each other, right? So I do think it's definitely, we definitely can tackle this, but it should be in the downstream components. So before we do the classification, we might want to do the speaker separation in the first place.
Okay. And do you also train with such a kind of data, like overlapping speech? Will that help?
No. So I think that kind of breaks. Well, it would be an interesting to try, but I think it kind of contradicts the original assumption of this model, right? Because again, when you have overlap speech, if you don't do any speaker separation, how do you obtain a clean speaker embeddings from one opposed to the other, right? You would have two speaker embeddings basically entangled with each other. So it's kind of hard to tackle that. So even if I want to include overlap speech in the pre-training, I would do a speaker separation in the first place.
Okay. And you assume that your entire audio is either real or fake, right? Like that is not like you can predict the regions where it is real and where it is fake.
So yeah, so in the paper, we are focusing on a binary classification, but then the pre-training framework itself, what we are proposing here is a representation, right? So you can use that representation for anything. So you can, if you have a downstream, let's say, localization model, right? It still can do the work. It's still just feeding in the representation into different downstream modules. If the downstream module is a binary classifier, it gives you a binary classification. If it's a localization module, it gives you frame level decisions. So it really depends on how you design your downstream modules.
Right. Okay. Yeah. Thanks.
No worries. Thank you for the question. All right. Carolina, do you have any practical example to illustrate the style linguistic difference between different? Yes, I do have that. I don't have that in the slide today, but I would encourage you to maybe check out the Neurobiz paper, because in the paper we do have spectrograms for some samples.
Okay.
And I can elaborate a bit on that for now. So for example, let's say for some samples, if we note, so one thing we notice is, let's say you have slightly longer pauses between words or like the end of the sentences, then usually the model is able to capture that. So it kind of falls into, you have the same, even if you have the same speech content, if you say that same thing using different rhythm, the model would be very, very good at capturing those things. So that's just one example. I believe I do have some other spectrograms in the paper. So yeah, feel free to check that out.
Okay.
Does
Thanks.
that answer your question? Or
Yeah. It's because I'm a forensic practitioner, so for me, this is
Yes.
actually very helpful to know, because a model as is not really admissible, so you kind of have to have these practical
Exactly.
examples. Yeah, but thanks. Then I'll check it. Thank you.
Thanks. Yixuan, thank you for yes, for emotion classification.
Yes.
I don't think you mean the backbone used for, are you referring to this XLSR backbone fine-tuned for SER?
Yeah, because that's speech emotion recognition, right?
Yes, exactly.
So because you want to, yeah, you go on.
Yeah, sorry. For that, we didn't fine-tune it ourselves. We were using a pre-trained backbone from Hugging Face, and I believe it was trained on IEMO-cap, if I remember it correctly. I can double check, but yeah, probably it was using IEMO-cap.
Yeah, I'm curious about that because IEMO-cap, I think they use voice acted to act the emotions. But
Yes.
I think you want to capture the real world scenario, how people's emotion correlate with their linguistic content. So I'm curious if
Yes.
we use in-lab data set, would that still be helpful to boost the
Yes.
performance?
So I think we are talking about two different training stages. So the SER model was an off-the-shelf, I would say, speech emotion encoder that was fine-tuned on IEMO-cap. And for our stage one, I'm not using IEMO-cap. I believe I was, for the EURES paper, I was aggregating data from Common Voice and Ravdis. I'm not if that's the correct way to pronounce it. It's another small emotional data set. And yeah, so for Common Voice, we don't have any emotion labels. The assumption there is that it's diverse enough to capture different, basically speaking, habits. Yeah, so we didn't have an IEMO cap samples in the stage 1 pre-training.
I see. So you just use that as a style encoder to extract the styles. It could be emotion or something else. Did I understand correctly?
Well, I think you're referring to the encoders themselves, right? So for that, again, here, the idea is that we want to decompose speech into different aspects, and we want to measure the alignment between them. And here I'm saying that we can use Style-LInguistics, but it could be something else. Simply because even if I use the first 11 layers for this XLSR model fine-tuned for speech emotion recognition, there still could be some other attributes, maybe even speech content contained in the first 11 layers, right? So it's very hard for me to say, hey, this is a fully disentangled style encoder. And I think this is quite a difficult assumption for any models, right? So yeah, so maybe we can change this to something else. I mean, as long as these should be two different aspects, it might work, right? Essentially, we only care about how they align with each other.
Thank you.
All right, we have Eugene said X vector model. Yes. Yes, I think what we have seen is that we see a lot of success from universal representations, right? So from these upstream encoders. And if you, let's say, use X vectors for deepfake detection, I'm not exactly sure how that would perform, but I think some studies have performed that kind of comparison. And usually what we see is that these, pre-trained SSL models usually give you better performance. And this was also the motivation why we think it could be interesting to do the pre-training ourselves. So yeah, it's hard for me to say if the future would just be developed from upstream encoders, but I would definitely say that pre-training there could be something interesting to be done in the pre-training stage.
Okay, thank you. And also, I'm curious for the model architecture. So
Yes.
before the binary classifier, did you put the embeddings? How did you fuse the embeddings?
It's simple concatenation. We do the average. We do for the dependency embeddings, they are already temporally averaged. For the output from the style-linguistic encoders, we pass them through the attentive statistic pooling to get basically the mean and variance, project into a lower dimension and concatenate into, so each of these, different colors here is 256 dimensional, and you concatenate them, it becomes a 1024 dimensional vector.
Oh, I see. Thank you.
Any comment about watermarking?
I think that question is for the webinar organization.
Okay.
I think Gerard is asking if we publish with watermarking on the video, if that's what it is. So Gerard, I assure you, I will convey this comment to the webinar organization, and we will ensure that we do watermarking so that deepfake cannot be created using these videos.
Well, that was not my question.
Okay, please go ahead then. Go ahead.
My question is, if we are going to impose legally the necessity of watermarking any audio or video that you put on the web, so that we don't have deepfakes anymore. I mean, that will destroy the deepfakes problem.
Yeah, I think watermarking and deepfake detection are addressing this problem at different layers, right? Watermarking is trying to solve this from the source. And I'm still a bit skeptical about how, if we can like 100% achieve that. At the same time, is watermarking perfect? Can we reverse the watermarking, right? So I think watermarking is definitely a solid alternative, or like one of the solutions that we can attempt. But at the same time, I believe it could be interesting to consider both solutions at the same time, because it won't really, well, nothing prevents us to do that, right? And I think at the current stage, it's a bit early to say that watermarking is destroying deepfake detection, because they're addressing this problem at different layers. So that's my thought about this.
Well, if you find an audio-visual file in the web, you can destroy it if it's not watermarked.
I'm sorry, I didn't get that comment.
I mean, any audio-visual file that you find on the internet could be destroyed if legally everything needs to be watermarked.
Well, then I think that boils down to how you want to do this watermarking. So let's say if I'm an attacker and I do have the modules, like I'm aware of how to train these generative models, and I synthesize somebody's voice and I use it to cause, to attack at the call center. And
okay,
how do you want to watermark it? It definitely can be, but then I definitely see that there's also some complications there. It's not as simple as we now add watermarks to every voice uploaded to the web. It's also about real-time calls, right? Yeah. So
yeah,
I think it's definitely worse. Yeah, go ahead.
Yeah, the attacker will have a hard time to generate the watermark because it's encrypted. So it's very difficult. Anyway, that's another topic. Thanks for your talk.
Yeah. I get this question a lot. So
okay,
watermarking versus deepfake detection, which one should we do? I believe worst case scenario, we do both.
yeah, okay.
That would be the safest option for users, right?
Right. Yeah. Thanks. Thanks very much.
Okay. So yeah, thank you everybody for the great questions, and thank you E for patiently answering all the questions. So this is the end of our webinar. So everybody, let's please take a moment to thank E. I think there is a react button and you can clap to virtually clap.
Thank you all for listening to the talk, and please feel free to reach out to me if you have any questions.
Okay, so I will just stop the recording.